So I'm going to plan to tackle antibonding. So first, to kind of get the concepts of antibonding, you need to know, well, at least for me, I think understanding some things like its rules help, but understanding why it's happening makes even more sense. So we'll start off with molecular bonding. We'll do an example, H2. This one's kind of dead. Hopefully that's what we're going to start off with. And here, I'll use gold. I'm going to use gold and silver. So H2 is a hydrogen plus a second hydrogen, right? And they each have one electron, and they form to make H2. They each have one electron right here. When they form, they kind of form like this. This is an electron, and this is an electron. They combine together to make H2. Or single bond double H. So they each have their orbitals. This one has an electron on the 1s, and then this other one also has one electron on the 1s. And then together they make H2 with 2 electrons on the 1s orbital. Just like that. And that is the core idea. Obviously, that's just a short summary. I don't think I needed to do that, but it's fine. It's whatever. Let's look at their protons right now. So we have this hydrogen that has this first proton, and it has one electron. And then we have this other hydrogen and its proton with its one electron. And we're going to focus on the forces at play. I'm going to use some colors for this. So first off, this proton is attracted to this electron right in front of it, and it has a force going this way. It's also attracted to this electron, and it's being attracted to 2 things to the right now. However, it is being repelled by this proton, and now it's going left. However, this is a very weak connection because obviously this proton is farther away than either of these 2 electrons. And that same logic is going to apply for this proton. It's going to be attracted to this electron and this electron, while at the same time it's going to be repelled by this proton. So we have 2 forces going to each other and 1 force going apart, and that works for both. And so the net force is going to be towards each other. Once this is all cleared up, the net force is going to be towards each other, like this. That is regular bonding, right? And when they do bond, they have their orbitals combine and look like this. And in here, there's 2 electrons. That's regular bonding. Now we're going to go into antibonding. All right, let's think about it like this. I'll do the two orbitals again. Let's say we have this first orbital, this first proton. And then I'll just do the negative sign to show this, right? Okay, so let's say these are our 2 electrons for hydrogen. Remember, before, when they bonded, these 2 orbitals created this larger orbital. And it has this electron wave in between them, right? When these 2 come together, they're going to make this little funky shape, like this. And in here, all of this empty space is what's called a node. And in a node, there are no electrons. So it's the exact opposite of the electron cloud, right? And so when we think about it, if there's no electrons here, our 2 hydrogens would not look like this. This would be wrong. Instead, their electrons would be on the outside because, again, of the node right here. So let's look back and act as if they're protons. We have the 2 protons right here, and now their electrons are on the outside, okay? And I'll go through the forces again. I will use cool colors. So let's look at this proton first. It's being attracted to the electron right here, and therefore it has a force going to the left. I'm going to say going outside versus inside. Outside versus inside. It has the attraction to, it's being repelled by this proton, and again, that means that it is being repelled outwards. And finally, it is attracted to this electron, and it's being pulled inwards. But again, this electron is farther out from the proton and this other electron, so it has a lesser effect. And now we'll look at this other proton. It's being attracted to its electron right here, and it's being pulled outward. It's being repelled by this other proton, and that means it's being repelled outward, and it's being attracted to the electron on the other side, and it's being pulled inward. So we have on each 2 forces going outwards and 1 force going inwards. So the overall force between these two is going to... What the fuck is going on? Sorry, I don't know if I can pick up on camera. I just heard people yelling so loud, like they were gonna die. So the net force is going to be repulsion, just like this. Again, it's similar to this. In these, the electrons were on the inside, and they had 2 forces going inwards and 1 force going outwards. That led to a net force of attraction. Here, remember the node, the electrons can't be in the middle, they have to be on the outside, like right here. Therefore, their net force is going to be repulsive, right? Okay. So let's do a little summary in this corner right here. Let's do bonding versus anti-bonding. I'm just gonna leave it as anti, that's good enough. So when their two are in a bonding molecular orbital, their electrons are on the inside, right? And they're gonna come together to create something like this. One thing. And in here we have their electrons. And now take a moment and remember their forces. I think I did red. Their net force is going to be attracting. When we do anti-bonding, however, their electrons are on the outside, like this. And they're going to come together. And they're going to have a node in the middle, just like that. And remember here, no, that's the wrong color. There you go. Their electrons are going to be on the outside, like this, because of the nodes. And their net force is going to be repulsion from each other. And that is going to kind of explain why this happens. It's not yet explaining how to solve the problems, but at least for me, this really helps me understand. It helps me understand and visualize what's going on when I'm reading the problems. So hopefully this helps you too. Now, the next thing is going to be getting into how to solve. I'm going to start off with solving for bond order. Let's look at this example. I'm going to use hydrogen again. It's really easy. I'll probably do some other examples towards the end. We have our first hydrogen, and we have, goddamn, I have to recap all these pens. We have our second hydrogen, and they're going to come together to make H2. So this first hydrogen occupies a 1s orbital, and it has 1 electron, and this second hydrogen also occupies a 1s orbital with 1 electron. Let me do something. As this goes up, energy is going to increase. So when these two orbitals merge together, they're going to make, I'm going to do orange and yellow, I think, yeah. So they're going to make this 1s, I think it should be right. Yeah, this is going to be sigma 1s, and up here, this is going to be sigma 1s antibond. And remember, anytime there is a asterisk, that means anti-bond. Hopefully the yellow is showing. I think it is. Cool. So, as you know, everything in the universe wants to be at the lowest energy level. It wants... Oh, I'm dropping my pens, all my pens. It wants to be at the lowest energy level it can be. It wants to spend as little energy as possible. That's why I'm watching this video. I'm so funny. Anyways, so it's very easy to go from a high energy level and drop downwards, which is what this one's going to do. It's going to drop its electron downwards, and so is this other hydrogen. It's a lot easier to roll a ball down a mountain than to roll it up a mountain. And so they're going to fall into this 1s orbital. And they're going to bond. So now we're going to calculate bond order. This is going to equal, so to solve for this, you're going to have your number of, let me do this in orange, number of bonding electrons minus the number of anti-bonding electrons. And take all that, and you're going to divide it by 2. This Sharpie's dying. I'm not using it anymore. Take all that and divide it by 2. And so let's look at hydrogen. So I'm going to move these out of the way. They're cluttering your view. Let's look at hydrogen. They have 2 bonding electrons and 0 anti-bonding electrons. So when we solve for this, their bond order, or their BO, is going to be 2 minus 0 divided by 2. That's going to equal 1. So let's talk about what 1 means in terms of bond order. When a bond order is equal to 1, it usually means a single bond, right? And I say usually because apparently there are some cases where it doesn't always mean this, but I really haven't found any. If it has 2, it means double bond. And if it's 3, it means, obviously, triple bond. If it equals 0, then it means it can't bond, or like it's unstable. Can't bond. And if it has a decimal, anything with the decimal is lone electron. So that's what these all mean. And hopefully this is going to clear it up a little bit. That's how you calculate your bond order, and that's how this diagram is going to work. I'm going to go find an example to give you for something that's not hydrogen. All right, here are some example problems we can do. Let's start off with, let's go with helium, He2. Now, helium is a halogen, and this can't form. So antibonding can kind of help explain why. So we'll start with, actually, I need to get, here's my periodic table. Hold on. All right, so again, we'll do gold and silver to represent the 2 types. So we have the helium here, and helium occupies 2 electrons in the 1s suborbital. And this other helium does that same thing. And so let's remember, let's do a diagram down here. We'll put 1s, sigma 1s, and antibond, sigma 1s. And remember, energy is increasing as, why did I write a 5? What the fuck? Energy is increasing as we go up. So let's start off with this first helium. It has 2 electrons here, and the second helium has 2 electrons here. Now what it's going to want to do is, again, remember, it's going to drop to the lowest energy level it can. And so this one's going to drop on here, and this one's going to drop on here, and that's going to lead to a filled 1s orbital. However, they each still have 1 electron, and so these need to go up a level, and they need to go to antibonding, right? And so now they're filling the sigma 1s and sigma antibond 1s. So let's try to solve for the bond order. We have the number of bonding electrons, which is 2, and we're going to subtract the number of antibond electrons, which is 2, and we'll divide it by 2, right? And this is going to equal 0, and 0 makes a lot of sense because, as we know, helium-2 can't form. And so this is a step to explain. All right, for the next example, I'm going to do one from our homework. It's going to be C2 2-, and this is actually kind of going to help because I was low-key a little bit confused on ions, but they're nothing special. It's literally just add 2 electrons. But I'm just going to do this. I think it like kind of tackles a little bit of everything, you could say. I think it'll help. So let's take our first carbon, and it has 4 valence electrons, and it occupies 2 electrons in the 2s suborbital, and 2 electrons in the 2p suborbital. And that is the same. That goes the same for this other one. So remember, each carbon has 4 electrons, and we have 2 of them, but we're going to add 2 electrons because it's negatively charged. And so that's going to give us a total of 10 electrons to work with here. So let's start our diagram. At the bottom here, we have sigma 2s, and then here we have regular 2s right here. Duh. And then at the top here, right above that, we have antibonding 2s. Then above that, we have our pi 2p right here and right here, and above that we have sigma 2p, and here we have our regular 2p orbital, 2p sublevel. Now above that, again, because antibonding takes more energy, so above that we have we have our antibond 2p, and above that we have our pi antibond 2p. Okay, so at the very bottom, sigma 2s, regular 2s, and sigma antibond 2s. Remember, it takes less energy to bond than it does to do an antibond. We have 2p, we have our sigma and our pi orbitals, and right above are anti-sigma and anti-pi orbitals. It takes a second to draw this diagram. You don't really have to. It's on this pink sheet, and you can kind of almost do it in your mind, in your head. It's not too hard. So let's start filling this in. On this first carbon, it's going to be, these carbons are going to be filling the 2s and 2 2p's. Remember, always fill out each section before you pair your electrons together. Very important. So first, let's take a look. These 2 electrons are going to fall to a lower energy state because it's easier and occupy this suborbital. But then, once this is full, they need to occupy the antibond orbital right here. I'm going to leave that there. And when they do that, there, now they're antibonding and bonding, and it's going to kind of cancel out. So here, next, what we do is, these here are going to fill up right here. And, sorry, that should go, that's, you know, it's going to fill up this one, and this, sorry, and this one. And then this one's going to do the same thing, right here, right here. And there we go, there's our molecular orbital diagram for, oh, hold up, I'm stupid. I forgot about our 2 extra electrons. Silly me. I'll just do that in black. That's going to go one right here, and that's gold. Fuck am I doing? One right here, and then we'll do one right here. Something like that. We'll put both on this side. How about it? So for our bond order, we have 1, 2, 3, 4, 5, 6, 7, 8 bonding orbitals. I'm going to -2. Sorry, minus our 1, 2 anti-bonding orbitals. Divide all that by 2, and we get a bond order of 3. How about it? And there we go. That's how you do this with ions. Again, you just have to add in the electrons. This whole little chart is kind of unnecessary if you have the pink chart, this pink paper, or if you can just do it in your head. It's honestly not too challenging. Hopefully this helped. If you guys have any requests, I'll do. I don't know. I don't have much to do tonight.